Yeah. So, in case there is any doubt or you want to ask anything, even if it's in between, so please don't feel shy to interrupt me in between and ask it straight away. No need to raise hand. Just unmute yourself and ask it at the time. Okay. Uh,
Okay, sir.
so I will start this session. So this is basically the NPTEL river engineering course, and this is going to be the first weekly session of it. This is an initiative of NPTEL and the Swayam scheme. Uh, and this course will be tutored by Professor Subhashish Datta, who is from the Department of Civil Engineering at IIT Guwahati. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship at the Interdisciplinary Center for Water Research in IISc Bangalore. I believe someone is trying to enter the room. Yeah, he entered anyways. Yeah. So I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship at the Interdisciplinary Center for Water Research (ICWR) at IISc Bangalore. So before starting today's talk, just want to mention that all the video recordings which I would be taking from these weekly sessions will be uploaded almost immediately after the class in this YouTube channel, River Engineering TA Abhishek Chakraborty. So in this, I would be uploading all the video recordings of it. So the assignment zero has already been uploaded there. Apart from that, all the files which I will be showing during this course of 8 weeks, I will be uploading them to the Google Drive folder. The address is also given there. The address of the YouTube channel as well as the Google Drive folder will be very shortly given to you over emails too. Anyways, I've already written the folder's address and the YouTube channel's address here, and I will make sure to upload the files as well as the video recordings right after the class ends. Although, I mean, in case there is some issue with the internet or something like that, then even after that, I will try my best to upload the files as well as the video recordings by the end of the day. So this lecture starts from 6 p.m. to 7 p.m. I will try my best to upload it before midnight. So no need to worry about that. Yeah. So. Before starting the class, I would just give you a brief overview of what was explained in the second lecture about the sediment properties in the class. Uh, we understood that as we transition from the upland reaches uh, to the fluvial plains and finally to the lowland reaches, the river properties change a lot. They change drastically, in fact. The sediment properties change from erosion dominant at the upland reaches of the mountainous zones mostly, to that of transportation dominated in the fluvial plains, to that of the sedimentation dominated in zone 3, which is near the ocean. The bed also changes its properties from a degradation bed based bed to that of an aggradation based of bed, which happens after an equilibrium. And the channel most of the times are confluencing at the upper reaches, and they happen to be branching at the lower reaches. The slopes transition mildly from a steep slope, or gently from a steep slope to a flat slope, moving from zone 1 to zone 3, and the transition happens to be of that of a mild course in most of the cases. And the bed material also transitions from a cobble gravel one to a gravel sand one, and finally to a sand silt one as a river reaches near the oceans. One thing which is very interesting in this part is the geological property of the bed. What are degradation and what is aggradation? Uh, and what's the difference between them? I would like to give this a brief overview so that I can explain finally why a river usually forms. What kind of properties are required for a river to form and to flow? So, So these two are basically nothing but I'm very sorry. Yeah, these two are nothing but geological processes. That is, they usually take a lot of time for happening. Usually ranging from thousands to millions of years. In However, the time frame depends over for different rivers around the world. So I will just give a brief difference between aggradation and degradation. After this slide, I will explain why are these processes so important for the formation of a river. So mostly aggradation, as it was already discussed by Professor Datta in his lecture, it basically relates to the increasing. Uh, Basically, it increases the bed level of the river, whereas degradation results in decreasing the bed level. Aggradation happens in sediment-rich rivers, whereas degradation happens mostly in sediment-starved rivers. So aggradation is associated with deposition of sediments, deposition of sediments, whereas degradation mostly is associated with erosion of the sediments or the erosion of the bed, river bed. And last but not the least, aggradation is mostly associated with a decrease in kinetic energy, whereas degradation is associated with an increase in kinetic energy. I will take just one more slide to explain it. So a few things are to be noticed. What is the role of the kinetic energy? How does kinetic energy play a part in aggradation or the degradation? Basically, as rivers run out of kinetic energy, that means that whenever the stream velocity decreases, they they lead to a deposition of sediments. Deposition of sediments. I believe someone is trying to enter the room. Yeah. So as the kinetic energy of the rivers decrease, that means that as the stream velocity decreases, it leads to a deposition of the sediments because they don't have enough energy to keep the sediments entrained in them. So you know that there are several kinds of sediments in a flowing river. Some of them may be heavier, and some of them may be lighter. The lighter sediments usually don't get deposited at all, even at lower speeds. However, the heavier sediments, they may get deposited at the bed as the velocity decreases. So this velocity change is governed by several factors, uh, mainly by seasonality. For example, let us just look at a peninsular river. Let us say Godavari. So you would expect that for Godavari, the stream flow would be much lower during summer seasons than the monsoon or the post monsoon seasons, because the river is not rich in water, and hence the flows would be much low during the summer periods. So as the kinetic energy decreases, the deposition of sediments also happens more, because they don't have enough energy to keep the sediment entering. So this leads to deposition because the kinetic energy has been lost, and this deposition leads to rising bed level of rivers. The bed levels rise because the sediments are already deposited there. So this thing that is aggradation, it's more commonly seen in braided rivers. So braided rivers you might have seen in most of the Indian rivers. When they reach towards the oceans, the braidings increase. The rivers may be very wide, however there may be several sandbars in between. So these are what we call as braids, or the braiding of river. There may be number of sandbars in rivers as they reach the ocean. The Jamuna River of Bangladesh is a very common example of it. So in braided rivers, you will see that the stream velocity drastically decreases, and that is why the deposition of sediments, it also increases, leading to the braided rivers. And these are also known as sandbars or gradings. There are several names for it. So it creates a braided appearance for the river. So there are another reason why the braided rivers may be formed. The other reason are riverine plants. Riverine plants, or the plants which are near the fluvial surface, the stream surface. What they do is that they may take the root in the river, creating an area resistant to erosion where sediments can build up, creating a bar. So as the plants or vegetation increase near the banks of the river, their roots may penetrate deep into the banks of river. So it will cause more resistance to the flow of the river, and that is why more sediment deposition will occur, resulting in higher number of bars in that area. On the other hand, the process of degradation is a completely different process. We'll take another slide to explain that. Yeah. So degradation happens when the kinetic energy is high, and kinetic energy can be high because of several factors. Some of them may be probably because of a higher glacier melt in case of rivers which are fed by glacier melt, or there may be steepening of the river slope by tectonic uplift. So this steepening may happen over a course of millions of years, or abruptly due to heavy earthquakes. So this due to this increased kinetic energy, entrained sediments are not able to settle at the bottom of the river. So that is the major difference between aggradation and degradation. Okay. Uh, if you have any doubt, please feel free to ask me. You can just unmute yourself and ask me that question. I mean, till this point, is there any doubt or anything to discuss?
So,
Yeah, sure.
so you said in the first slide, like degradation happens in a sediment-starved river.
Okay.
Okay, can you just explain with respect to this last concept, actually, degradation with respect to the kinetic energies?
Okay. So when the sediments are more, there would be more probability of them getting settled down at the river because of several processes, because the stream flow discharge is not constant throughout the year. It will vary a lot. Okay. Like for Indian rivers, the monsoonal periods exhibit the highest stream flow discharge. Do you agree with that? Because of mostly
Yes.
the pluvial input or the rainfall input into the rivers. Okay. So when there is a lean period, the probability of decomposition or deposition of the sediments increase. Okay. So that is why this was said that it mostly happens in sediment starved rivers. If the sediment load is more, then the probability of decomposition will anyways be more, because there are several lean periods for a river, seasonality wise. Like for the rivers of northeast India, especially Brahmaputra, the winter periods are the lean periods. It means that it does not rain a lot during that time, and that is why the discharges are pretty low when you compare it with the discharges of the other months. Okay, am I clear to you?
Yes, sir.
Okay. So I will proceed then. there is one doubt there. You all must be having a very simple doubt, that why do we need this course of river engineering? Why don't we just merge this course with fluid mechanics, just like the case of open channel hydraulics? Why can't we just why do we need a separate course, uh, separate study material for this course? What's so different about it? We're just doing the same thing as fluid mechanics, isn't it the case? I mean, what do you think about that? Any idea why we need a separate course on river engineering? Any idea? Please feel free to share your thoughts. Yes, please proceed. Any idea why do we need a course on river engineering?
Yeah, the riverine hydrology is different when compared to fluid mechanics actually.
Yeah, so but can't it
So
be defined by the water transport itself?
no, yeah, my view actually, whenever we are designing something over that river, we should know the in detail about the hydrological part of that river. Actually, that's
That is a very correct view. I will just add to that a very different process of sediment transport also occurs in rivers, apart from the water transport. Of course, water transport is also a very prominent feature of river courses, but sediment transports also occur, and that is why river engineering is such a distinct course. Okay, I will explain it using some mathematical formulations now. First of all, why do rivers form? This is a question which may have come in mind of many people. Very common question. So, we and in terms of rivers, I'm mostly talking about the alluvial rivers in this case. So alluvial rivers are the ones which in which the bed and the banks are made up of mobile sediments and or soil. So the sediments are mostly present in alluvial rivers, and most of in most of our country, the rivers are mostly alluvial in nature. Mainly the North Indian alluvial plains. So the major rivers of India are alluvial. Are present in alluvial plain. That is, they are defined by a mass transport of sediment in their basins. So three of the most important rivers which feed the stomachs of billions of people in India happen to be Indus, Ganga, and Brahmaputra. All of them are actually in the alluvial plains itself. So it becomes very important to know why such rivers actually form, and which is the more dominant process governing the formation of such rivers. Is it aggradation or the degradation? So I will take just another slide to start this mathematical formulation. So let us just take an example of a confluencing river. So it means that the width of the river decreases. Let us just assume that this is the top width, the top view of a river. It is flowing like this, and there are two sections to the river. Section 1 and the converging section 2. So let us just assume that in section 1 the width of the river channel is 2W, and in section 2 the width of the river channel is W. So we are just assuming, just to explain why do actually rivers form and which process govern the formation of rivers among aggradation and degradation. I will explain it using this example of a river which uh, converges to half of its width as we move further towards it. So there can be two different components of river. One component may be the water component, the other component will be the sediment component. So both these components are very essential for river hydraulics, and that is why we need to be concerned about both of them. So the water component from the continuity equation will give us that the discharge at Q1 at reach 1 1 will be equal to the discharge at reach 2 2. This is nothing but this is a very fundamental of continuity of mass conservation. So Q1 will be equal to Q2. And for sediments, we know that sediments may be defined using or may be taken as a function of the stream flow discharge like this: A times q to the power b, where small q, this small q is nothing but unit discharge. So unit discharge is nothing but q by h, that is the total discharge under the unit head, and qs will be the unit sediment discharge. As I told you that there are two separate processes which govern the flow of rivers. One is the flow of sediments and the other one is the flow of water. So we need to be concerned about both of them. And let us just assume that C is the sediment concentration. So for the upstream section, let us suppose the upstream section, as the river is moving uh, from the top of the page to the bottom of the page, we can take the upstream section as 1 1. For the upstream section, we can write the total sediment load at 1 1 as equal to the sediment unit discharge, that is QS1 at 1. This subscript determines that it is for reach 1 1, multiplied by the total width of that reach. So the width is 2W for this case. So, and as QS is equal to A times Q to the power B, that is, we are trying to write it in terms of water discharge or water unit discharge, we can write it like this: A times Q1 to the power B times 2W. And let us suppose Q1 is equal to Q, Q1 is equal to Q. Let us just assume it for the moment. So we can write this expression as 2W A Q to the power B. So this will be the total sediment load at 1 1. Let us again take the total sediment load at 2 2. So that is the downstream section. So this would be again Q1 times 2W or Q2 times W, because as Q1 is equal to Q2, we can write Q1 times the width 2W equal to Q2 times the width there W. So Q1 times 2 is equal to Q2, that is the relation we will find from here. Q2 is equal to 2 times Q1. So it will be the sediment load at 2 2 will be Q2 times the width there, that is W, or the Q1 times the width 2W. So both are same. This can also be written as the width times, now we are just explaining it in terms of water discharge, width times the coefficient A times 2Q to the power B, because we took Q1 equal to Q. We'll take another slide to finish this formulation, and I will give a very interesting result out of it. So we got finally that at 1 1 and at 2 2 the sediment loads are different. The sediment load at the total sediment load at 1 1 is 2W. W is the width at that position times 2WA times Q to the power B. and at reach 2 2, it would be WA times 2Q to the power B. So we see that these two sediment loads are not equal. They are not equal. So any idea which quantity would be more among these two? 2WA times Q to the power B or WA times 2Q to the power B. So which quantity will be more? Any idea about it? It will depend on the magnitude of B, right? The coefficient B. Whatever is the coefficient B value, that will determine which of the left hand side and the right hand side is more. So we can partition the values of B into two different components. If B is less than 1 and if B is greater than 1, if B is less than 1, then we will get, if B here is less than 1, so what will we get? Which side is more, the left hand side or the right hand side? Yeah, so the left hand side will be more in that case, right? So if B is less than 1, then we will see that there is a lesser sediment transport capacity at 2 2 than 1 1, and vice versa happens when B is greater than 1. So this is effectively the case of channel aggradation, because it's decreasing, and this is the case of channel degradation. So what happens is that in very simple terms, and just to summarize this thing, I will take just one final slide. Without any mathematical formulation, I will explain finally. So as we move to a converging river, that is, as the width decreases, if the sediment load here at the right hand side, that is in the second reach 2 2, is less, load here is less than that of the left hand side, then the channel has aggregated aggradation has happened, because this means that already a lot of sediment has deposited somewhere in between, and that is why the sediment load has become much lesser as we move from reach 1 1 to reach 2 2. And if the opposite happens, if the sediment load is uh, more here, if the signs reverse, if the trichotomy reverses, then it would be degradation. That means that this more sediment has crossed on and reached sediment reach 2 2. Why? Because a lot of erosion may have occurred in between. So that is the basic funda behind whatever I'm trying to explain so far. So this was the first thing. Now, why? I will just come back to the previous question. Why do rivers form? What is so necessary for the formation of rivers? Why do rivers form? So the thing is that for a river to form, flow convergence, just like the case I showed here. So this was the case of converging flow. So for river to form, flow convergence must be preferable to flow divergence. Why? Because then the aggradation will not happen most of the times, because from experimental evidences also it has been found that B is mostly greater than 1 for a sediment to discharge relationship. So so when we sum it up, we will get that flow convergence must be preferable to flow divergence for rivers, Or if flow convergence would result in aggradation, then the sedimentation process would force the water away from the point of convergence and rivers would never form. So rivers can only therefore form when flow convergence results in river flow degradation. So that is why degradation is such an important process for the flow in a river to be possible. I hope I am clear so far. If you have any doubt, please feel free to just stop me in between, because after this I am going to start the numericals, which will not require the concepts from here, but still I wanted to give you this idea. Is there any question? Okay, I guess this you don't have any doubt. So let us just take a set of questions as we proceed into the lecture. This question is very similar to the last few questions which would be available in your assignment 1 of this course. Uh, the flow duration curve of two gauging stations of a river with a reservoir storage as given in figure 1 is given in table 2. So this is the table. This is the table 2 in our case. So this is table 2 and this is figure 1. The sediment duration curves of the stations are also tabulated below. Okay. So what are the questions? The questions start here. A flood of 5% time exceedance probability has passed through the 8-day duration. The total amount of flood water at reach 1 in million meters cubes are okay. So we are asked about the 5% exceedance cube, exceedance probability. So let us go back to the question. So we can see that there is the percentage time of exceedance plot. It is given for 0%, it is given for 10%. However, 5% is not given. So what do? We can take a simple arithmetic mean to find out the q at a 5% time of exceedance. Okay. However, it is not something which is recommendable, but we can still do it because of lack of data in this question. So 5% Q is not given. So let us just take it as Q corresponding to 0% excess plus Q percentage corresponding to 10% excess by 2. That is the arithmetic mean of the two. Okay, so this would turn out to be the sum of these two quantities, that is 3200 plus 3000 meter cube per second by 2, so it comes out to be exactly 3100 meter cube per second. So this question wants you to find a flood of 5% time exceedance probability which has passed through for an 8-day duration and the total amount of flood water. So we just want to convert this 3100 meter cube per second into million meter cube. So that is the objective of this problem. So we can just multiply this discharge with the time to get the final volume. It's as simple as that. So the procedure would be 3100 meter cube per second times 8 day. However, the units are not consistent. In the left hand side there is second, in the right hand side there is day. So we have to finally convert it into meter cube and then into million meters cube, which is equal to 10 to the power 6 meters cube. So this can be written as 3100 times, convert the days into seconds. So each day will have 24 hours, each hour will have 60 minutes, and each minute will have 60 seconds. So now we have it in meter cube. Okay, and just divide by 10 to the power 6 to convert the meter cube into million meters cube. So the final answer will be 2142.72 million meters cubes. So that's the answer to the first problem which I have discussed here. The second problem is that a flood of 5% time exceedance probability has passed through for 8-day duration. the total amount of sediment load at reach 1 and reach 2 in kg is? Okay, it's a very interesting question, but it's for the sediments and not the discharges. Okay, before proceeding into it, I would just want to put light on two different factors. So, station 1 was upstream of the reservoir, and station 2 is basically downstream of the reservoir. So, due to that, effectively, most of the sediments may get deposited in the reservoir itself, and that is why ideally we should see the sediment load at station 2 to be much lower than that of station 1. Also, another simple logic is that as the discharge increases, that is the water discharge increases, the sediment concentration should also increase, because more of the sediment proportion will be entrained in water as we have higher discharge. So we do see very similar, I mean, whatever we inferred, we do see similar numbers in the table also. So let us just take a higher discharge quantity. That is let us say 3200 meter cube per second. So corresponding to that, the sediment concentration is 420 milligram per liter. As we move into a lower discharge, the sediment concentration also decreases, which is quite according to the logic that as the sediment discharge increases, the sediment entrained number will also increase, and that is why the sediment concentration should increase. The second thing is the that what happens because of the reservoir. Does the reservoir play any part? So we can clearly see that the sediment concentrations have decreased. So let us just take the sediment concentrations with respect to the same discharge. So the discharge is, let us say we take the 3200 meter cube per second discharge for reach 1 as well as for reach 2. So we can see that the corresponding sediment concentrations have decreased a lot for reach 2 than that of reach 1. Why? Because a lot of sediment may have already been trapped by the reservoir. So we can see that the sediment concentration at reach 2 is almost half that of the one at reach 1 for 3200 meter cube per second. Now let's just take another concept. What happens due to the interplay of the discharge and the sediment concentration? So and the reservoir presence. So what happens because of that? So I will explain it using a lower discharge quantity. So let us say we are taking a lower discharge of 160 meters cube per second for reach 1 and reach 2, we can see that the sediment concentration has decreased a lot with respect to reach 1 to reach 2. So it is basically a 6 times decrease for the reach 2 sediment concentration than that of the reach 1 sediment concentration. So the 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 inference is that as the discharge decreases, more of the sediment will tend to deposit in the riverbed, and that is why more of the sediment concentration will also decrease, and the presence of reservoir will actually uh, decrease the sediment concentration even further. So these three inferences I wanted to first of all discuss through these tables. I have done that. Let's now move back to the question. A flood of 5% time exceedance probability has passed through the 8-day duration. The total amount of sediment load at reach 1 and reach 2 in kilograms is. Okay, so we need a 5 percentage. So basically, the funda behind this question is that we need to multiply the water discharge times the sediment concentration to get the final load in kilograms. Okay, so this can be done like this. So first of all, we need to find out the 5 percentage time exceedance probability discharge for reach 1 and reach 2. Let's go back to the table. Yeah, so for reach 1, it will be found out by the arithmetic average of 3200 and 3000, and for reach 2 also the same. So the discharges have not changed because of water mass conservation of water. So Q reach 1 at 5 percentage exceedance can be written as the arithmetic average for 0 percentage exceedance and the 10% exceedance. This is not preferable, but due to lack of data, we need to take the arithmetic average only. So this would be arithmetic mean only. So this would be 3100 meter cube per second. In a similar way, we can also find out the concentration at reach 1 at 5 percentage exceedance by taking the arithmetic average. So we need to take the arithmetic average of 420 and 410 for each one, and 220 and 200 for each two. So this would be 420 plus 400 by 2, that is 410 milligram per liter for each one. So Q reach 2 is equal to Q reach 1 also, because of water conservation, the mass conservation. But the sediment concentration will be the corresponding sediment loads, the sediment concentrations for for, I mean, the will be found out by the arithmetic mean for the 0 percentage exceedance and the 10 percentage exceedance discharges. So this would be 220 plus 200 by 2 equal to 210 milligram per liter. So now we want to find the total amount of sediment load at reach 1 and reach 2. So let's find it out. It's very simple. So for reach 1, it will be, as I told you already, it will be a multiplication of the discharges. First of all, we need to convert the discharge into mass, into volume by just multiplying the time duration. So this would be 3100 meter cube per second into 8 day, 24 hours, 60 minutes, 60 seconds. So we have converted it into meter cube, and again convert this 410 milligram per liter into kg per meter cube. So 410 into 10 power minus 3 will make it into gram, into 10 power minus 3 will make it into kilogram. So this would be kilogram per 1 liter. So, and 1 liter is equal to 10 power minus 3 meter cube. So at reach 1, the sediment load will be 8785.152 into 10 power 5 kg. So it's a big number. It's a big number actually. We'll take just one slide more to explain the rest of the question. Let us just talk about the reach 2 now. Reach 2 again, we know the discharge already, we know the sediment concentration already, so it's pretty straightforward. 3100 meter cube per second into 8 day, 24, convert into hours, convert into minute, convert into seconds, meter cube times 210 milligram per liter. So just multiply it straight away by 10 power minus 6 to convert into kg, and we need to convert the per liter into per meter cube. So 10 power minus 3 meter cube. So this happens to be 4499.712 into 10 power 5 kilogram. So you can observe that the sediment load at reach 1 is 8785.152 into 10 power 5 kg, and at reach 2 is 4499.712 into 10 power 5 kg. So the sediment load at reach 2 is almost half that of reach 1. And why has that happened? Because most of the sediment may have already got trapped in the reservoir. Okay, so let's move to the next question. For the flood of 15 percentage time exceedance probability, the sediment trap efficiency in percentage of the river is for 8 day duration. In percentage of the reservoir is for 8 day duration is. So this question is basically two steps. Number one, we want total sediment load at reach 1 and reach 2 both, and finally we will calculate the sediment trap efficiency in percentage. So sediment trap efficiency in percentage will be nothing but total sediment load at reach 1 minus total sediment load at reach 2 by total sediment load at reach 1 into 100 percentage, just to convert it into percentage. You don't have to report it in ratio because the question requires that. So that is the thing. So let's just see. So what will be the total sediment load at reach 1? We will find it using the very similar technique which we used in the previous question. So corresponding to 15 percentage time exceedance probability you want, and 15 percentage I believe is not given, so it will be taken as the arithmetic mean of the discharges corresponding to 10 and 20 uh, percentage time of exceedance. So we will do the same. So total sediment load at reach 2 will be, okay, the first of all the arithmetic mean, then multiply this sorry, convert this discharge into volume by by multiplying this discharge by the time duration, that is 8 days. So we have to convert 8 day into seconds, and we have to again multiply it by the arithmetic mean of the sediments present there for the 10 percentage exceedance and the 20 percentage exceedance. So that is 200 milligram per liter and 180 milligram per liter. So we have to convert it into kg. So multiply by 10 power minus 6, and liters you have to convert into meter cube. So divide by 10 power minus 3. So it happens to be 2954.88 into 10 power 5 kg. I will take another slide to finish this. Yeah. So at reach 2, we have already found out what is the sediment load. We need to find out the sediment load at reach 1. Load at reach 1 is equal to 3000 plus 2000 by 2, that is the arithmetic averages of the discharges. Convert the 8 day into seconds, then take the arithmetic mean of the corresponding 10 percentage exceedance and 20% exceedance sediment concentrations, that is 400 milligram per liter and 320 milligram per liter. Convert it into kg to 10 power minus 6 kg by 10 power minus 3 meter cube. So the answer would be 8709.12 into 10 power 5 kg. So the sediment trap efficiency finally will be sediment load at 1, 8709.12 into 10 power 5 minus sediment load at 2, that is 2954.88 into 10 power 5 by sediment load at 1, 09.12 into 10 power 5 into 100, just to convert into percentage, and that would come out to be 66.07 percentage. This means that almost two-thirds of the total sediment has been has been trapped by the reservoir. So the reservoir plays a huge role in trapping the sediments. So let's move into the next question. For a year of 365 days, the annual water storage in million meters cubes of the reservoir is. So this is a very interesting question. But one thing to be noted is that the discharge value is not given. So how would you convert the discharge into units of volume, that is million meters cube? So let us just see what happens. So we can see that there are in the original table we have been given the percentage time of accidents and the discharges corresponding to that, and but the discharge for the annual period is not given straight away. So what will you do? So usually what happens is that the discharge is taken corresponding to a lower time of accidents, because for most of the years the discharge is not at the extremes. So it will definitely not be at 0% time of accidents, 10% time of accidents, 20% time of accidents, or 30% time of accidents. So usually for, I mean, we can just assume the discharge to be corresponding to, let us say, 70% time of accidents or 80% time of accidents. So these higher discharge values will only occur under certain flooding based periods. However, that is definitely not the annual average discharge. So when you compare the different types of floodings in river or in Indian rivers, you will find three different types of floodings: the pluvial flooding, and the ocean based coastal based flooding. So I will just give a brief about that. Flooding can be either fluvial or pluvial or coastal flood. So in the fluvial based flooding, what will happen is that they can only occur because of tidal backwater and some upstream discharges. Probably there has been observed to be a higher melting of the glaciers from which the water comes to the system, and that is why uh, the fluvial systems have become submerged in water. So this fluvial flooding happens because of that. Pluvial flooding, that can occur because of heavy local precipitation, or in technical terms known as extreme rainfall events. So ground cannot absorb the rainfall effectively, and that is why this kind of flooding occurs. The third, or or fluvial flooding can also occur for urban drainage systems when they are overloaded by excessive water flow. And coastal flood can occur, why? Because of inundation of the land areas along the coast by seawater. So it can be caused by compound events. Compound events means when two extreme events can happen together. So the compound event may be higher rainfall and high tides. If they both happen together, let us say for a 6 hour period or an 8 hour period, then this coastal kind of flooding will occur. So these are the three kinds of floodings. For most of the Indian river system, the the flood I mean, mainly the North Indian rivers are fed by glacier melting, and they are perennial in nature. However, the peninsular rivers, when we just exclude the Western Ghats, they would be mostly not perennial in nature. And during the summers, the discharges decline a lot. I am excluding the Western Ghats because the Western Ghats happen to be some of the most rain-fed regions of our country. So when we compare a peninsular river with that of a North Indian river, we can see this: the frequency, frequency is nothing but the number of times this happens of the discharge will vary a lot. So for a peninsular river, it may look like this. So higher discharge events will be less frequent, whereas the lower discharge events will be more frequent. So this will be peninsular for peninsular rivers, and for North Indian rivers, since North Indian rivers are fed by the glacier melts of Himalayas, so they are perennial. So the frequency to discharge may look like this. So the lean period discharges will not be. I mean, most of the time the discharge will not be very low and not be very high. It will be in between. So that is a difference primarily in the discharge distributions of peninsular versus that of the North Indian rivers. Okay, so for this question, we have not been given the discharge. So what would we do? The discharge is not given for a 365-day period. That is for the annual period. So we can just assume that uh, assume it to be somewhere. I mean, the mean annual discharge percentage time of exceedance can be taken from anywhere between 50 to 100 percentage exceedance for discharges for a river. So high, it will of course depend on the geography or the bed form of the rivers too. So higher discharge events only occur during extremes, as is the case, and we call it as the right tail. We usually call it as a right tail. So these extremes may be probably because of higher localized precipitation, higher localized rainfall, or some sudden discharge of urban water into the river flow, which may result in flooding of the system. So we, in this case, are taking the discharge corresponding to 80 percentage exceedance. We can take it anywhere from 50 to 100 percentage exceedance, but we are just assuming it the annual discharge, the mean annual discharge, to be corresponding to the 80 percentage time exceedance discharge. So we will solve it in the next slide. Yeah. So we take the 80 percentage, and the sediment concentration with respect to 80 percentage will be 200 milligram per liter, and the discharge with respect to 80 percentage exceedance is 180 meter cube per second. You will find it from the table also. So the question requires the annual water storage of reservoir in million meters cubes. So just multiply the discharge by the time, that is 365 days, multiply it into hours, multiply the hours into minutes and the minutes into seconds. So we get meter cube from it, and just divide it by 10 per 6 to get the million meter cube quantity. So, so that would be 5676.48 million meter cube, the annual water storage of the reservoir. Next, let's proceed to the next question. So, for a year of 365 days, the annual sediment storage of the reservoir is. This is again very similar. We already found out the sediment concentration, that was 200 milligram per liter, corresponding to 80 percentage exceedance. Just multiply this volume into that of the sediment concentration. So we get the final answer to be 5676.4048 into 10 per 6 meter cube was the volume. Multiply it with the concentration. So 200 milligram will be converted into kilogram by multiplying it by 10 per minus 6, and the liter will be multiplied into meter cube by multiplying into 10 divided by 10 per minus 3. So the final answer will be 11352.80 into 10 per 5 kg. So this is the final sediment load, the annual sediment storage of the reservoir in kg. So we are almost on time, but I will just give a brief recap of what we learned today. We started off with the two basic geographical processes which govern the formation of rivers, that is the aggradation and the degradation. We then moved into a brief discussion over why the rivers would form, mostly in alluvial settlements and alluvial rivers. We finally found that the degradation is essential for the rivers of the converging kind. Then we solved a few questions to find out primarily the volume and the sediment concentration. We also learned what might be the effect of change in the time of exceedance, the effect of the reservoir, and the decrease or increase in the discharge on the sediment concentration. So these are the basics which we learned today. Uh, if you have any question, please feel free to ask me. Is there any question?
No, sir, for me it's very clear.
Okay, okay. So the last few questions which I solved, through them you can also solve the last few questions of assignment one. Assignment
Yeah,
one should be very easy. I mean, after
from
this.
11 to 17 questions
Yeah,
from.
exactly. That should be very easy. I just change the numbers.
Yes.
So you can just change the play with the numbers and find the final values. Just a brief about the assignment. I believe in the last question about sediment properties, I think question number 7 or 9 something. Uh, you just need to I mean there are four options given, right? So you, and the answer which you will be getting may not completely match that of that with the options. So you just need to take the option which is nearest to your answer. Okay. And
Okay.
take G, that is the acceleration due to gravity, as 9.81 in your analysis and not 10. So it should be 9.81 grams sorry, 9.81 meter per
Mm,
second square. So you will get the answer. If the answer is if none of the option is matching, then just tick the option which is nearest to your answer. You will get the correct answer. So
okay.
I am done with this session. Any other doubt, or shall we finish it now?
Oh,
Okay, so I think that it's we are done for the day. Thanks a lot for joining.
thank you. Thank you, sir.
Yeah, thanks a lot.